Graph each function. All right, so you notice the first function is an exponential function. F of x is equal to 2x. And the second function is a logarithmic function, which is basically log of x base 2. So notice that the base of this log function is the same as the base of the exponential function. That means these two functions are inverses of one another, because the inverse of the exponential function is the logarithmic function to the same base. All right, so if that's the case, then let's go ahead and plot the exponential function first and use that graph to derive the inverse function, which is going to be the log of x base 2 here. So let's start with a little table of values, x and y. We'll use the classic values, -2, -1, 0, 1, and 2. All right, let's see what those give us when we enter them into our function. If you have 2 to the -2 power, that's the same as 1 over 2 squared, which is the same as 1/4. So this one will be 1/4. 2 to the -1 is the same as 1 over 2, which is 1/2. 2 to the 0 is just 1. 2 to the 1 power is 2. And finally, 2 squared is 4. So we'll have 4 there. All right, let's go ahead and plot these points. And keep in mind that we have a horizontal asymptote for this graph at y equals 0, or in other words, the x-axis. Remember, this function here can never achieve the value 0 and can never be negative. Okay, so let's look at -2, 1/4. That might be here, let's say. And then at -1, 1/2 would be here. At 0, 1, we'd have a point here. At 1, 2, we'd have the point here. And finally at 2, 4, we'd have the point here. Okay, and then if we connected those in a smooth line, basically get something on the order of that. Okay, let's go ahead and graph the logarithmic graph by recognizing that the two functions are inverses of one another. That means we can just simply switch their x and y components of these points, right? So whenever we had -2, 1/4, that would be the same as having 1/4 -2 on the graph. And it'll be 1/2 -1, and 1, 0 instead of 0, 1, and 2, 1 instead of 1, 2, and finally 4, 2. So those will be the points for the logarithmic graph. So for x equals 1/4, -2 will go out about 1/4, go down 2, so we're about here. And then we'll go out 1/2 and go down -1, so that's here. Then we'll go out 1 on the x-axis, but go nowhere on the y-axis, so that's here. Then we'll go 2, 1, so out to 2, up 1. And then lastly, we have 4, 2, so out to 4 on this axis and up to, that's about there. And again, if we connect them in a smooth arc, we get roughly this graph, and it'll hug this. All right, so remember some things about this function here. Here we have a vertical asymptote because x has to be what? Strictly greater than 0. So this graph has an asymptote here that we have listed for the y-axis, and that for the exponential function we'd had this axis, right? This horizontal axis for the exponential function. So the exponential function has a horizontal asymptote, the logarithmic function has a vertical asymptote. Remember that both of these lines have to be symmetric to this line, right? Because essentially they're inverse functions of one another. So if you folded the rectangular coordinate system along that diagonal of y equals to x, right, we would end up seeing these two graphs lay on top of one another, and that's basically what it looks like is happening here. So of course we've shown visually that these two functions are indeed inverses of one another, and we found a very easy way to graph the log function, which is basically to graph the equivalent exponential function and then switch the points around because the two functions are inverse of one another. So this gave us a great way to graph logarithmic functions. We basically would graph the related exponential function and then switch the points around in order to graph the logarithmic function since they are inverses of one another.